afternoon. So today I'm going to present for you our project entitled Design of Multiscale Hetrostructures. So our research team is our Dr. Marwan Al-Haik, me, Najib Mazbouni, and our PhD student in our group, Amir Ali Skandani. So our research topic is basically how to scavenge energy from damping of a large composite structure. So we have an FRP composite, and then we are trying to embed zinc oxide in the FRP composite and see how can we scavenge energy from this composite. So we are suggesting basically to grow carbon nanotubes and zinc oxide and carbon nanotubes with zinc oxide on the top of woven carbon fiber, conducted pitch carbon fiber, and see how the growth of zinc oxide and carbon nanotubes improve the mechanical properties of the woven carbon fiber, and then we'll try to profit from piezoelectric properties of the zinc oxide nanorods that we are growing for energy harvesting applications. So our research is interdisciplinary, and it covers many ICTAS mission areas, including nanotechnology, nanomaterials, mechanics, renewable energy harvesting, and nanomanufacturing. So the developed materials, which is FRP with zinc oxide or FRP with zinc oxide and carbon nanotubes, can have many future applications like aircraft, cars, sporting goods, and wind turbine blades. So first we start with the growth of carbon nanotubes, of zinc oxide. So the growth procedure here is a hydrothermal synthesis technique. So we are putting the woven carbon fiber in a chemical solution composed of HMT and zinc acetate. So we start with varying the parameters in the growth procedures in order to come up with the optimal parameters. So the optimal parameters here that we have chosen is 4 hours of growth at the concentration of 0.04. So with these parameters, we got 1 micron, as we see here in the SEM images. We got 1 micron nanowires, and we see that the nanowires that we are growing are uniformly distributed on the surface of the carbon fiber. So with this, we started testing the mechanical properties of the FRP. So the first test was the off-axis tensile strength. So we have prepared 4 samples. The first sample is neat, meaning carbon fibers without growth. Then we have sputtered a layer of zinc oxide. Then we have used a layer of the same sputtered layer, but we have put it in the same experimental conditions than the growth sample, meaning the water at 4 hours at 80 degrees Celsius. And then we have prepared a sample with the growth. So the growth sample is FRP composite with zinc oxide on the surface of the carbon fibers. So as we see here, we get very good results. And we see here that if we compare the growth sample, sample with zinc oxide, to a neat sample, we get 25% improvement in the off-axis tensile strength. So 25% of tensile strength between the carbon fiber without nanowires and the zinc oxide sample. So our explanation here is that the adhesion between the nanowires and the epoxy is good. And then we believe that the interaction between the nanowires, from the opposite faces, and the epoxy is much better than the properties of the carbon fiber itself with epoxy. So that's why here we get better results in the off-axis. So in addition to that, we see here that the nanowires facing each other will induce more friction in the structure. If we have more friction, of course, we get more damping. And if we analyze here the damping properties of our sample using the dynamic mechanical analysis, the DMA, we see that here that the 10 delta, which is a measure of the damping within a viscoelastic material, we get 20% improvement between the growth sample, the green one, and the need sample. So we get 20% improvement in the 10 delta, which means that we are improving the damping properties of our structure. So with this, we think that growing zinc oxide on carbon fiber will be advantageous for structural damping applications. So this is for the mechanical part. After that, we have moved to testing the energy harvesting properties of our samples. So we have fabricated an energy harvesting device composed of 2 layers of carbon fiber, 1 glass fiber in the middle as an insulator, and then we have sputtered a copper layer on the zinc oxide, which will be used as electrodes. So, and then electric wires will be attached to the copper layer. And then we have tested the energy harvesting device in an open circuit voltage. So here in the red is the reference sample, which is, we see that there is no piezoelectric effect or no energy harvesting in the energy. The green one is the sample with zinc oxide. So we see here that the voltage reached about 0.1 volt. This is an open circuit. So this basically shows us that there is an energy harvesting for our device. So here after that, so this is an open circuit voltage. So we think that the next step will be to optimize the structural layout of the device in order to improve the voltage here and then the energy harvesting, energy harvested. And then we're thinking of using a vibration shaker table in order to control the frequency, the excitation frequency. So we will think of excite the device at the resonance frequency and see how the varying the frequency will affect the harvested energy. So the next step is to grow carbon nanotubes on zinc oxide. So basically we have succeeded to do that experimentally. We see here that we have the zinc oxide nanorods with carbon nanotubes covering basically the nanowires. So if we look here, so those are the carbon nanotubes covering basically the zinc oxide nanowires. So here we are trying to profit from the outstanding mechanical properties of carbon nanotubes and the good electrical properties of the carbon nanotubes, and see how growing those carbon nanotubes will modify the mechanical properties of the composite and the energy harvesting characteristics of the FRP. So we have potential sponsored research opportunities from NSF, Department of Energy, and Boeing. As a highlight, we have succeeded to grow zinc oxide nanorods in a controlled fashion on the surface of carbon fibers, or with a uniform distribution. So the surface grown zinc oxide improves the FRP's damping, as we see in the DME results, and the off-axis mechanical properties. We've got up to 25% improvement in the off-axis tensile strength. So we have succeeded to create the FRP carbon nanotubes and zinc oxide heterostructures experimentally. And then we're thinking of building a molecular dynamic model in order to see how embedding zinc oxide in composite structure will alter the vibration properties of the composite. So so far we have published 2 papers, one about the enhanced vibration damping of carbon fiber zinc oxide nanorods, and one about the hybrid carbon fiber carbon nanotubes composite. We still have 4 more articles in preparation. As an intellectual properties per pending results, a patent will be filed in May 2013. So we'll be organizing an ASME session in November 2013 for heterostructured nanomaterials in San Diego, California, and one PhD dissertation in next May 2014. And then we have submitted 2 conference papers for the ASME conference. As funded projects, we have a supplement through current ONR project. We have $50,000 to compare zinc oxide to carbon nanotubes effects on damping and mechanical properties. And then we have an NSF proposal will be submitted in October cycle. And then we are currently in current talks with the Department of Energy Office of Science. Thank you for your attention.